Hey, this is a new thing I'm going to try out because I thought, why not make video solutions to these instead of writing up about 50 pages in one channel? It'll definitely condense stuff, and hopefully it'll be a better explanation for some of you guys. So please bear with me, tell me if there's anything that I may want to improve, and I'll just go on with the problem. Okay, so first let's let n be a positive integer. The p-value of n, denoted pn, is the number of digit sums needed to reduce n to a single digit. Now, if you don't know what that means, I've put a few examples here. So, for example, the classic 69, its digit sum is 6 plus 9, because we have 6 and 9, which is 15. So we've done one pass, and now 15, its digit sum is 1 plus 5 equals 6. And you can see that we've done two passes. So its p-value, so the p-value of 69 is 2. Okay, and clearly 203. So just because a number is bigger doesn't necessarily mean that its p-value is bigger. I mean, clearly 2 plus 0 plus 3 is 5. So p of 203 is 1. And clearly p5 is 0 because it's a single digit. And we're looking for the smallest n such that pn equals k. So that's what pk is defined as. And now the actual question's asking, given that a, b, c are positive integers, and we have this p5 is equal to sum a times 10 to the b minus c, what's the smallest that a plus b plus c can be? Well, let's start off simple. Let's try the value of p0. So this means that it has, in fact, it has to already be a single digit because we don't do any digit sums, and it has to be a positive integer because that's what n is. And in fact, that's clearly 1. That's the smallest. Okay, so what about p1? Well, p1, we know that it has to not be a single digit, and well, the smallest number that's not a single digit and is positive is 10. And in fact, p1, so the digit sum of this is 1 plus 0 equals 1. Okay, that works out. So what's p2? Well, we can probably work out a few extra values. So 1, 1, so 11, 2, and 12, 3, 13, 4. And let's go on. Well, we have 18 is 9, and then 19, well, that goes to 10. But 10 isn't a single digit. So then if we sum that again, that goes to 1. And well, that took us 2 jumps. So we can safely say that p2 is 19. And it's quite weird. It's almost as if p2, the digit sum of p2 is p1, and well, the digit sum of p1 is p0. So does that pattern continue? I mean, let's see. Assuming the pattern continues, that means that we must have a mystery number, so p3, we don't know what it is yet, and it goes to end up being something plus something plus something, because this could actually go on for a while, we don't really know. And we know that it is equal to 19. Well, let's consider a digit. A digit can range from 0 to 9, and we want to sort of minimize the amount of we want to minimize the value of the number. Let's try thinking of some single digit numbers that might sum to 19. Well, for example, we could have 7 plus 7 plus 5. Yeah, that's 19. We could also have 4 plus 9 plus 6. Yeah, that's 19. But we sort of want to have the smallest. We want to have the smallest possible value such that it sums to 19. Firstly, when we have 7 plus 7 plus 5, the best way to arrange that is 5, 7, 7. So we're arranging the digits in ascending order. And, well, clearly we want the larger digit to be at the back and the smaller digit to be at the front. That will minimize the number. We can also sort of shift these along. So what I mean by that is this 5, 7, 7, we can put this 7 up to an 8, and then in fact subtract 1 from the 7, and we'd still have the same value. So 5, 6, 8 will give us the same digit sum, but it would actually be a smaller number. And if we think about this, we can actually just have 199. And again, 199 is 1 plus 9 plus 9. And you can actually check this. This does in fact turn out to be the smallest number with this p-value. Okay, we're almost there. We need p4 now, and then from p4 we can get to p5. So p4, well, it's whatever sums up to 199, and it's the smallest number that does that. So one way you might like to think about this problem is putting balls into boxes. So let's say that each box has a capacity of 9 balls. Okay? Well, how do we arrange it so that we're being quite efficient with our boxes and generally with our space? So we'll start by filling up the first box here. So here we have, let's say we have 19 balls to distribute, and so we have 5, 6, 7, 8, 9. Yes, this is definitely big enough. We have 1, 2, 3, 4, 5, 6, 7, 9, and we have 1. And this is our 19 balls, and this is how we got our P3, which is 9, 9, 1. Okay, so we can try a similar tactic for P4. We'll need to distribute 199 balls into these boxes. And we can use the same analogy in order to get P4 using P3. So with P3, we have 199, let's say we have 199 balls. The boxes are still the same, so the boxes are at most 9, representing the digits. So, how many boxes do we need? Well, we need 199 divided by 9 boxes. And this turns out to be 22, remainder 1. And this is because we have 199 is 198 plus 1. And 198 is just 99 times 2, which itself is 9 times 22. Cool. Now, because we have 199 divided by 9 is 22 remainder 1, this means that we definitely need 22 full boxes. Okay? So these are full of 1, 2, 3, 4, 5, 6, 8, 9 balls. And so these have 9, and there are 22 of them. Cool. And we also need one box which has 1 ball. And this is 1, and we just have 1 of these. So, because of this, our P4 must be 1, and then I need to count this properly. 9, 9, 9, that's 3 9s, 6 9s, 9 9s, 12, 15, 18, 21, and 22. So this is 1 with 22 9s, or rather a 23-digit number. And you might think, oh god, if this is P4, what is P5 going to be? And yeah, P5 is quite big, but we don't have to give P5 as is. We have to give P5 like this, in this form. So we need to figure out what's going on. And in fact, this balls and boxes analogy might serve to help us quite a bit here. Okay, so how is P4 expressed in this answer format? Well, we can write P4 as 2 times 10 to the 22. So this is a 23-digit number, and then we just take 1 off it, because this is like 2, 0, 0, 0, 0, 0, 0, 0, 0, minus 1. And, well, we can also express this in a similar way to how we've expressed P3 before, as, well, it's 2 times, and, well, it's quite a lot of 9s. You have 9, 9, 9, 9, 9. And this should be 22 9s. And we actually add 1 to this. Now, P3 is surprisingly useful for actually finding out this P5, because if we consider what we did in order to find P4, well, we did 2 times 99, which this is repeated twice, plus 1, and then we divided it by 9 to find out sort of the boxes and balls that would fit in. And this becomes 2 times 11 plus 1 over 9, which is clearly 22 plus 1 over 9, so 22 remainder 1. Why don't we apply it to this? Okay, so let's try dividing this by 9. And when we do that, we get 2 times 1, 1, 1, ba, ba, ba. And again, there are 22 of these ones. And again, we get 1 over 9. So, in fact, when we divide by 9, we get 2, 2, 2, 2, ba, 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 ba. And this is remainder 1. And there are 22 of these. And in fact, this goes straight into the power, like it did with last time. And we can write P5, the one we're actually looking for here, is, again, 2 times 10. And then it's actually this big number, so it's 2, 2, 2, 2, 2, 2, 2, 2. Okay, and then we want to minus off 1. And, well, it says here, what is the smallest that A plus B plus C can be? And currently, we have A plus B plus C equals, well, 2 blah, 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 repeated like 21 times. And then at the end, we need to add 2 and 1, so 5. Keep in mind the minus here. Now, is this a minimum value? Well, the biggest thing, quite clearly, is this 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. So in order to make it smaller, in fact, let's knock off 1 off the power. So if we knock 1 off the power, what do we have to do with it? 2, 1. Well, if we do that, we have to sort of put it into the A. So then this becomes 20, and in fact, our sum becomes bigger. And that's not what we want, because we've taken 1 off from the power. We've actually added 18 here. So not a great start. Okay, so let's try taking off a power and adding to the minus. Well, no, we can't add to the minus, because if we take off a power, it'll only become smaller. And since A, B, and C need to be positive, that won't quite work. If you try a few more cases, you can see that this is in fact the smallest that A plus B plus C can be. So our final answer, which is of course 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 5. Now, I know what you're thinking. This is a very horrible sequence. Did you just make this up from the spot? Well, surprisingly no. This is actually a real sequence. This is called the additive persistence of an integer. You can actually find it in the OEIS. So that's the Online Encyclopedia of Integer Sequences. And, well, I think you can imagine how big P6 and onwards are going to get. So, did you find this video helpful? Please let me know, and if there's something you want me to add, or maybe you want me to go through a bit slower, or try a few different approaches, just feel free to let me know. Thanks for watching. I'll put up another, hopefully easier, question today.